now let's talk about residues. So the residue is this coefficient right here, the C minus 1 coefficient, the C minus 1, that's the residue. Okay, so that's the main thing. Also, the reason that this is important is because of theorem 7, 9, 10, the residue theorem. So if F is holomorphic in a region G except for isolated singularities and gamma is a positively oriented, simple, closed, piecewise smooth path that avoids the singularities and is contractible to 0, then there are only finitely many singularities inside, and the integral of the line integral of F around gamma is equal to 2 pi I times the sum of the residues. Okay, so here we have a picture of what's going on. So here we have a function F that is holomorphic everywhere except for these residues here. And then this gamma goes around the whole thing. Okay, and basically each one of these singularities has, when you expand it, it has a Laurent series expansion. And you find the C minus 1 term for each one of these, add all those C minus 1 terms up, that's the sum of those residues. The integral is going to be 2 pi I times that sum. Okay, so that's why everything's important. And the proof is kind of interesting. You can basically take this curve and deform it into little curves that go around everything. And then, okay, by using the idea that the function F is holomorphic everywhere, that it's not going to a singularity. Okay, down here, it gives you, so this residue theorem is really important. Here it gives you a way of finding singularities. It just dismisses if your residue, if it's a removable singularity, then the residue is just 0, okay? So you don't have to worry about that. If it's a polar order n, then here's how you can find it. This is a formula you can use, but I'm not gonna go through the formula. Instead, I'm gonna show you a few different ways of finding residues. I'll give you a few examples, okay, of several different residues and how to find them. Okay, so first of all, and we'll do some integrals as well. So the first one I want to do is find the residue of F which is 1 over z times sine z at 0. Okay, so the first thing that you should do is try to figure out what kind of singularity is. So first of all, what singularity do we have at 0?
0.
Yeah, 0 is a singularity. What is it? Okay, so the choices are removable, pole of order n, or essential. So the first step is to figure out which one of those it is. Okay, do you guys remember?
A pole.
Yes, it's a pole. And what's the order? Now that's the order is probably the most important part.
1.
Okay, it's actually, that's tricky. It's tricky. It's actually order 2. Because this is 0, but this is also, yeah, the sign. So when you multiply two things that would normally give you just a polar order 1, then you get a polar order 2, like that. Okay. So it's order 2. Okay, so once you get this number right here, then what that tells you is that if you expand it in a Laurent series about 0, then the first term is going to be that one. Okay, so this is telling you that we're going to start here, and that's going to be your first term. Okay, now of course, to find the residue, that's going to be this one. Okay, so this is the one we're after. Okay, now think algebra, or algebra and calculus. And we just want to find this term. This is the term we want to find. We just want to find out what this number is right here. And so, I suppose I shouldn't do this. I should write this as 1 over z sine z. Yeah, so there we go. Okay, so now I have this equation here, which has to hold for all values of z. And I want to find out what this is. So how would I go about doing that? Does anybody have an idea? Okay, let me get you started, okay? Multiply both sides by z squared. Okay, and that will give us, okay, multiplying this by z squared is going to give us z over sine z over here. Over here, we're just going to have c minus 2. So we get that now. Multiplied every term individually by whatever that is, okay, which came from here. From the order 2 gives us a z squared, and then leading off with a z squared in the denominator. I multiplied by that, and I got this. Okay, now remember, our objective is still just to find this one. We don't need to find anything else.
Take derivative?
Yes. Derivative. Differentiate both sides. Because over here, this goes away, I just get c minus 1. Okay. So I just get a c minus 1 there. Over here, I can just go back to calculus. So low d high. So the denominator times the derivative of this, which is 1, minus high times the derivative of low. So that would be z times the derivative of this is cosine c, all over the square of what's below. So that would be over sine squared of z. Okay, now normally what I would do is plug in z equals 0, right? But it gives me a 0 in the denominator here. Okay, so that's kind of awkward because I should find, this has to be, or this is going to be a nice number. But over here, when you plug in 0, you don't get anything. You get like 0 over 0, right? Okay, so when you get 0 over 0, then you think, okay, why don't I just take the limit? And that's where my c minus 1 is going to be. It's going to be the limit of that, of this right here, as z goes to 0. Okay, so if you plug in, again, you get 0 here, 0 there, and 0 there. So you got 0 over 0. So what do you feel like doing right now? So you're probably like, this is really fun now, right? Because guess what we get to do?
The Rachets rule.
Yes, L'Hopital's rule, right? L'Hopital's rule. You're probably just woke up this morning and were like, whoa, life was so much fun back when we were doing calculus 2 and we were doing L'Hopital's rule. I wish those days could be back, where our math was much easier. Okay, so the derivative of this is cosine, and the derivative of that is, okay, sine. The derivative of sine is, or z is 1, so that's cosine z. And then, oh, good for nothing. Okay, so z times the derivative of that, so that's going to be z sine z. And then down here we have 2 sine z times the derivative of sine z, which is cosine z. And now these guys cancel out, right? And then this sine z is going to cancel with that one. Okay, and then now we can plug in. And what happens when you plug in z equals 0 here?
0.
And then this is not 0, right? So this is 1. No, what the heck? This is 0. Okay, so the answer is 0, or the residue of f at 0 equals 0. So the residue is 0. Okay, so that's one way. If you can identify the order of the pole, and then just write it like this, and then start taking derivatives until you isolate that term. And then until you have it just down, until you have like c minus 1 plus a bunch of stuff multiplying by z minus z naught, then you can just set z equal to z naught, wipe all those out, take the limit here, and you got it. Okay, that's essentially, so what I just showed you is essentially using this formula here with n equal 2. Okay, pole of order 2 is basically take, so instead of, so the derivative, you're taking the n minus first derivative. So we took, n was 2, so we took just the first derivative, and we took that limit. That's what it was. Okay, so that's essentially what we did. Okay, so let me show you some more finding residues. So let's find the residue of, okay, well, this time I'll have g of c, cosine c over z to the 5th at 0. Okay. So what what is the order of what is the singularity at z equals 0?
0. And is a pole in order of 5?
Yeah, it's a polar order 5. So we could do the same thing as we did last time. That would work. That's one route that we could go. Okay, and we find eventually it's going to be a c minus 1. And so we'd multiply both sides by z to the 5th. Take a bunch of derivatives until we get down to the c minus 1 term, and then set z equal to 0, right? Or take the limit as z goes to 0. But it's probably it's just going to be, because it will just be cosine z, then we're just going to be taking derivatives of cosine z. So that's one way. But here we have another option that we could try. And that would be to exploit this fact, to expand cosine z into a series about 0. So what's the series involving cosine z? Instead of writing like a summation sign and write out, just start writing the terms. So the first term would be 1, and then what? It's minus
z,
what?
Z squared over 2 factorial.
Yes, exactly. And then the next one is
Z to the 4th over the 4 factorial.
yes, and then z to the 6th over 6 factorial. Okay, so which one of these? So if I take this and this one, if I multiply those two together, that gets me, that's taking this and dividing by z to the 5th, right? So I'll have 1 over 4 factorial over z. And so that means that the c minus 1 term is 1 over 4 factorial, which is, what is that? 1 over 24. Okay, so that means that that's what the residue is. Okay, and so I didn't need to go this route. I could have gone this route, taking 4 derivatives here, and multiplying by z to the 5th, then taking 4 derivatives. I could go that route, but I can exploit. But maybe it's easier to exploit this fact right here, that the cosine z splits up into all that. Okay, great. So now let's take a look at some more types of exercises. So the reason for finding residues is so that we can find integrals. Okay, so let's do this. Let's find the integral. Okay, this is the circle whose center is 3i and radius is 1. And we have dz over z squared plus 9. Okay, so it's always a good idea, it can't hurt, to draw a graph of what's going on. So where are the singular points? So if this is, so you're looking at f of z equals 1 over z squared plus 9. What are the singular points for this, for the singularities?
-3s and +3.
Yeah, those, okay, so 3i and -3i, right?
Mm-hmm.
Because when you put 3i in, you're going to get -1, and that's going to give you 0 in the denominator. Okay, so we have 3i, and we have -3i. Those are the singularities. This curve right here, this one, that is right here. And so the only singularity that's inside is this 3i. So we don't have to worry about this one. So we're only concerned about this one, the 3i. And so what's the residue of f at 3i? Okay, so first of all, what kind of singularity is it? Okay, so is it
Is that
removable, a pole, or essential? And what were we saying?
Removable.
What's that?
Removable.
No, it's not removable because when you put 3i in, you get a 0 in the denominator.
And pole.
Yeah, it's a pole of order 1. Okay, because if you take this, okay, this z squared plus 9 can be factored into z minus 3i times z plus 3i. Okay, so you can see that there's a factor of, there's a z minus 3i factory in the denominator, and it's raised to the first power, so that's a pole of order 1. Okay, so if you just factor this into here, then you see it. It's a pole of order 1. Negative 3i is also a pole of order 1, but that doesn't matter because you're not integrating about that. Your integral's over here. This radius 1 stays far away from here. It doesn't surround this one. Okay. So that means that 1 over, let me do this one. So 1 over z squared plus 9 is equal to, it's a pole of order 1. That means the lead-off term is this guy. No, that's not squared. And we want to find this term right here. Okay, so how do we find it? You have this equation. How do you find c minus 1?
Plug in 3i to c.
Yeah, you multiply by z minus 3i. So just multiply by the denominator here. Okay, the left-hand side, because your left-hand, this right here, 1 over z squared plus 9 is actually this. When you multiply by this, it just cancels that one out. And you have 1 over z plus 3i. Okay, multiplying this one by z minus 3i gives you that one. And then these ones just raises the power, right? Okay, and now what? Now what do we do?
3i.
Yes. So you set z equal to 3i. Okay, and that's going to give us 1 over, this would be 6i. And then all these are 0. 0. That's 0, that's 0. Everything else is 0. So that means c minus 1 is 1 over 6i. which is the same as -1/6i. So if you take, so I going from the denominator to the numerator is, so 1/i is equal to -i. Okay, so that means that the residue of f, if this is f, at 3i is negative, well, actually, let's do this. Sometimes we're just going to say it's 1/6i like that, okay? Hold on a second. So that means that the integral is now, okay, it's 2 pi I times the residue, or the sum of the residues of the singularities inside. So it's 2 pi I times over 6i. Okay, so then the i's are going to cancel, and you get pi over 3. Okay, so you get pi over 3 as the answer. Now, if we had a larger circle that includes both of these singularities, then we would find the residue here as well. And what you would find is that the residue is actually -1/6i, and so then those would add to 0, and so then the integral would be 0. Okay, so if you had a larger circle, the integral would be 0. If you had a circle that would contain both of these, I mean, if you had a curve that contained both of these, a simple closed curve, then the integral would be 0. Okay, so there's that one. Let's see here. That's another problem. Okay, so here I'm going to have the integral around this circle of center pi over 2 and radius 1. And it's sine z over cosine z times the exponential of z dz. Okay, so here's a picture. Circle of the center is pi over 2. Pi over 2 is about 1.5 something. So that's 1, and then 2. So pi over 2 is like right here. Because pi is like 3.14, and so if you add by 2, then you get 1.5, almost 1.6. And the radius is 1, so that means that it comes out to about here, and then over to about there, and up. Okay, now, so what we're going to do, what we want to do, is we want to label singularities with x's, all the singularities that are inside this circle. And of course, it has the positive orientation, which is the counterclockwise orientation. So what singularities do we have inside this circle? There are values that make this denominator equal to 0. Okay, so what values, so you're either looking for cosine z equals 0 or exponential of z equals 0. But the exponential is e to the x plus iy, which is e to the x times e to the iy, which this is never 0, by the way. That's never 0 ever. Because the modulus is e to the x, and e to the x is never 0. It's always greater than 0. Okay, so that's never 0. So where's cosine 0?
Pi half a.
Yeah, pi over 2. So it's a singularity right here. And then it's also 0 when you come over here to negative pi halves, right? And then another one over here at 3 pi over 2. But we don't have to worry about those ones because those are outside the circle. So it's only this one right here. Okay. So, so now we need to find the residue of f at pi over 2. And that's what the integral is going to be. It's going to be 2 pi I times the residue of f at pi over 2. By residue of f, we mean, by f, we mean this whole function here, sine z over cosine z exponential z. Okay, so what is the singularity? So first of all, I should say classify singularity at pi over 2. What do you guys think? This is kind of tricky because maybe I haven't really explained it very well. But does anybody have any? So if you get it wrong, that's no big deal because I don't recall ever explaining this very well to you guys. Maybe I did explain it, but maybe it's easy to forget. So pi over 2 makes the cosine 0, right? So cosine, what kind of singularities is that going to give you? Anybody want to answer? Well, maybe it's not so. Maybe it's really tricky. So let's do this, okay? Cosine and sine.
Isenso.
What's that?
Isenso? Is that Isenso? Singularities?
Yeah, it's a pole of order 1. Okay, so cosine and sine at every one of the places where there's 0, it's a 0 of multiplicity 1, which means if you take 1 over that, then it's going to be a pole of order 1. Okay, so a simple pole when you do that. The exception is if you had something like, look, this might be a little bit confusing when you come across something like just quick note over here. If you had 1 over cosine z minus 1, if you had that, this would be a pole of order 2 at 0. Okay, something like that would give you a pole of order 2. But if it's just straight up cosine z, or just by itself, not 1 minus, or something minus, which makes it 0, then it's going to be a pole of order 1. Okay? So that means, oh dear. That means that when you expand this out right here, your leadoff term is going to be this. Okay, then the next term is C2 times Z minus pi over 2 squared. Okay, so again, we are after this C minus 1 term right here. We're after that. And so what do? You multiply by this denominator, like that. Okay, so you have Z minus pi over 2 sine Z over cosine Z exp of Z. That's equal to C minus 1 plus C0 times Z minus pi over 2 plus C1 times Z minus pi over 2 squared, and so on. Okay, all the other terms have Z minus 2 as a factor. Okay. And so now we're going to plug in, well, you can't plug in you can't plug in pi over 2 because that's going to be 0, right? And that's going to be 0, so it's going to be 0 over 0. So it's the limit as Z goes to pi over 2 of Z minus pi over 2 sine Z over cosine Z exp of Z. Oh dear. That's 0 over 0, so we get to do L'Hopital's rule. And the numerator, take the derivative of the numerator, and that's going to be the derivative of this one times that, so that's sine Z plus this one times the derivative of the second part. The derivative of cosine is, derivative of sine is cosine. Okay, and then the denominator would be the derivative of this, which is negative sine Z exp of Z plus cosine Z exp of Z. The derivative of the exponential function is the exponential function. Okay, now, not 0. This is as you go to pi over 2. Sorry about that. Okay, so now we can plug in pi over 2. We get sine of pi over 2 here. And then when you plug it in here, you get 0. And down here, we get negative sine of pi over 2, e to the pi over 2. And then over here, we're going to get 0 right there. Okay, sine of pi over 2, well, those cancel. They're just 1 anyways. So that's negative 1 over e to the pi over 2. Or negative e, yeah, well, just negative 1 over e to the pi over 2. So now you take that and plug it into here. Okay, so the answer is going to be 2 pi I times negative 1 over e to the pi over 2. So it's going to be negative 2 pi I over e to the pi over 2. That's what the integral is going to be. Okay, so that's another example. Let me give you another example, one more example of what could happen. And that's this one right here, find the integral of, let's do this. Let's say z to the 4th sine of 1 over z. Okay, so over here, we have, the center is 0 and the radius is 1. So we're integrating around this circle here. And looking at this function, what singularities does it have? What singularities does it have?
Zero.
What's that?
0?
Yeah, 0. 0 is a singularity because you can't plug it in right here. Okay, so 0 is a singularity. And that's the only one because you can plug anything else in. Okay, so everything else is fine. So what kind of singularity is that? Does anybody know? Anybody know what kind of singularity that is? In the classification? Okay, that's what we call an essential singularity. Okay, so if you have an essential singularity, then you can't do it by like the method that I just showed you, by setting up a kind of a series, a kind of power series, and then taking derivatives and setting stuff equal to the value. Okay, so you can't do it that way. So what you should do is that what you can do is this. Look at it as z to the 4th times, and then sine z, you know how to expand sine z in a power series, right? So that means you can use the same principle to expand sine of 1 over z. Okay? So just as a side note, how do you expand sine z? What is that? You don't need the formula in closed form. We just want the terms.
Z minus.
Yeah, so z minus z cubed over 3 factorial plus z to the 5th over 5 factorial, and then 7 over 7 factorial, and so on, right? So that's how you do that. Okay, so if that's sine z, then sine of 1 over z would be 1 over z. Instead of the z, it's 1 over z. This one would be 1 over z cubed over 3 factorial, and then this would be plus 1 over z to the 5th over 5 factorial, and then 1 over z to the 7th over 7 factorial, and so on. And then what you can do is you're just looking for case you're just looking for this one. We have c minus 1 over z. Okay, so you have z to the 4th. This z to the 4th is going to distribute inside, right? Okay, but which one of these is going to give you something of this form?
The third one?
The third one, that one is going to do it, right? So that one is going to do it. If you multiply these together, you get a 1 over z, but that's over 5 factorial. So that means that c minus 1 is going to be 1 over 5 factorial, or 1 over 120. And that means that your integral is going to be 2 pi I times 1 over 120. So that 1 over 120 goes in here. And so that's going to be pi I over 60. Okay, so that's how you can handle essential singularities. Well, hopefully if you have an essential singularity, you can expand this out and then somehow get it this way. If you have poles, then that's a little bit more.
How
Then that's
about
more.
remove?
What's that?
How about removable? Do we do it the same way?
Oh, removable? Okay, if it's removable, then, so let's say, let me give you an example of removable, okay? If it's removable though, that's even easier because you don't even need to find, because the residue is going to be 0, okay? But let me show you that, okay? Okay, so let's suppose that we're supposed to find the integral, and let's suppose we have z to the third over sine cubed of z. Okay, so here, so sine cubed in the denominator normally gives you a pole of order 3, right? But there's this up here that cancels it out. Okay, the only place that it's messed up is at 0, right? So does that make sense? So in sine cubed in the denominator gives you a pole of order 3, but since we have this z cubed up here, that just cancels that out and makes it removable. At 0. That means that the residue is going to be 0. It's just going to be 0. Okay, so this is going to be 0. Or 2 pi I times 0, which is 0. So that means the integral is just going to be 0. And the reason for that is that with removable singularity, there exists a power series of a function that's holomorphic at 0, that's identically equal to this function everywhere except at 0. And you're only integrating around this curve right here, which it doesn't include 0. So you're basically integrating, this integral of this function is the same as an integral of the corresponding function that is holomorphic at 0. It has no singularities. It's holomorphic everywhere. And so Cauchy's integral formula just, the Cauchy's Rachets theorem says that the integral is 0. Okay, or Cauchy's integral formula also. You can get to the same conclusion. So that's just 0. Okay. Also, it says it right. It also says that right here, if it's removable, then the residue is 0. Also says it right there. Okay. Let's see here. Let me just go one more. Where can I find that? Okay, there's this proposition right here. We don't use that much. It looks kind of interesting, but don't need to necessarily worry about that much. Okay, so the next section is argument principle and Rachets theorem. And I want to just today we'll end it with this definition right here, which is meromorphic. So it sounds kind of like holomorphic. I mean, I guess maybe you might consider that it rhymes. Okay, so meromorphic means it's holomorphic except for poles. Okay, that's the definition of meromorphic.